You see, before we wander too far into the dark tonight, let me ask you something. Something simple and, well, something impossibly vast at the same time. How much of the universe do you think we've truly seen? Not how much we imagine, not how much we hope, but how much has actually reached our eyes after crossing billions of years and a constantly stretching cosmos. Because every time we build a new telescope, Hubble, Webb, the arrays on mountaintops and the ones drifting in orbit, the universe seems to expand. Not physically, though it does that too, but conceptually. What we thought was the edge turns out to be only a curtain. What we thought was the whole picture becomes a tiny glowing patch on an infinite canvas. And I suppose the most unsettling truth is this. We've only glimpsed less than 5% of everything that exists. 5%. The rest, 95%, is real, measurable, undeniable, and completely invisible. Dark matter weaving the cosmic web. Dark energy pulling galaxies apart. These things shape the universe, and yet we've never seen them, never touched them, never interacted with them directly. So it leaves me wondering again, what exactly are we looking at when we stare into the night sky? Is it the universe as it truly is, or only its faint reflection? And if most of reality hides itself so well, then, well, what else might lie just beyond the edge of what our instruments can reach? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, since we're sharing this journey through the hidden cosmos, tell me, where are you listening from tonight? It's always fascinating to see who's joining us from all around the world. So let's continue. When we look up at the night sky, there's this quiet illusion that everything we see is somehow the universe. As if the stars scattered above our heads were a kind of complete diagram, a finished map. But well, the truth is softer, stranger. The truth is that every time we build a new telescope, every time we sharpen our instruments or stretch our gaze a little farther, the universe doesn't simply reveal itself, it expands. Not because the cosmos is changing that quickly, but because our understanding is. And, well, that is where this story begins. With a simple but unsettling realization, we have only ever seen a small fraction of all that exists. A slice, a whisper, a pale reflection on the surface of something impossibly wide. We live inside a cosmic bubble nearly 46 billion light-years in radius, and we call this bubble the observable universe. But you see, the phrase itself carries a quiet confession that what we observe is not everything. It's just the part that light has had time to reach us from. Everything outside remains hidden, not because it doesn't exist, but because the universe is too young for its light to arrive. So, before we wander through the mysteries, we need to begin with something foundational. Something deceptively simple. The meaning of distance in a universe where space itself expands. Many people ask why the observable universe is 46 billion light-years across in every direction when the universe is only around 13.8 billion years old. Shouldn't the limit be 13.8 billion light-years? Or something close to that? And, well, the instinct makes sense. It's the instinct born from living in a world where distances stay the same, where a kilometer is a kilometer and a year is a year, and the route from your home to the horizon never stretches beneath your feet as you walk. But the cosmos is not Earth, and space is not a fixed stage. It stretches, it breathes, It changes as light moves through it. And, it means that a photon traveling for more than 13 billion years has not traversed 13 billion light-years of static space. It has journeyed through a stage that kept expanding even while the photon was mid-step. Like trying to cross a room that keeps growing as you walk, the finish line stretching ahead no matter how much progress you make. The result is subtle, but profound. The galaxies whose light left them 13 billion years ago are now far farther away, sometimes more than 30 billion light-years distant. And that strange inflation of distance explains why our observable universe reaches a diameter of about 92 billion light-years. It's not that light traveled that far. It's that space carried those galaxies away from where the light started. And, once we understand this, the observable universe becomes less like a photograph and more like a time sculpture. Every photon we capture from a distant galaxy is a message sent in a different era of cosmic history. From a universe that was smaller, denser, brighter, hotter. To look outward is to look backward. To see farther is to see earlier. So, the James Webb Telescope, when it peers at galaxies whose light began its journey just a few 100 million years after the Big Bang, is literally looking at a younger version of reality. The galaxies we see as small red smudges are, today, colossal structures, spirals, clusters, webs, drifting somewhere far beyond our current horizon. Imagine watching a baby photo of a person who is now an adult living beyond the edge of town. You know the baby grew. You know the adult exists. But you cannot see the adult. Not because they're invisible, but because distance, time, and circumstance block your view. That is the nature of our cosmic horizon. And, that is also the nature of our limitation. The observable universe is not the universe. It's just the part that has unveiled itself to us, the part light has carried to our eyes. But the universe beyond, the larger structure, the unfathomable whole, remains hidden for now. And, there is something strangely poetic about this, because it means every image we see from space is a relic, a fossil of light, a memory of moments long gone. The galaxies we admire through our telescopes are no longer what they appear to be. Their light is ancient. Their shapes have changed. Their stars have died and been reborn. Their black holes have grown heavier, and the galaxies themselves have drifted farther away, carried by the unceasing expansion of space. The very act of looking out forces us to confront that time is not a river flowing uniformly across existence. It is a landscape, and we stand on one ridge looking across valleys and mountains carved not by geology, but by the finite speed of light. So, what exactly is this boundary? The edge of what we can see? Cosmologists call it the particle horizon, the limit beyond which no light has had enough time to reach us since the beginning of the universe. And even as we speak, even as we breathe, this horizon expands by roughly 1 light-year every year that passes. But here lies the twist. The galaxies near this horizon are not merely far away. They are receding from us faster than the speed of light. And, that's not a violation of physics. It's simply space expanding between us. The cosmic fabric stretching so quickly that even light cannot bridge the widening gulf. You see? It's not objects moving through space faster than light. It's space itself expanding. It's not a race. It's a transformation. And so we find ourselves trapped inside a bubble whose boundary outruns any hope of catching it. No matter how fast we travel, no matter how long we wait, there will always be regions of the universe whose light will never reach us. Regions forever beyond touch, beyond knowledge, beyond observation. And, if that sounds melancholic, there is beauty in it too, because it means the universe is richer than we can ever fully perceive. Its complexity, its enormity, its structure, these are not confined to what we see. They stretch far beyond, into realms that time itself has shielded from our gaze. We often speak of telescopes as tools that reveal the universe. But perhaps, the gentler truth is that every telescope tells us how much we still cannot see. The deeper we stare, the more darkness unfolds. And yet, that is what draws us in, the not knowing. The sense that the cosmos is not a solved puzzle, but a living mystery, larger than our imagination. So, when we talk about the observable universe being 46 billion light-years in every direction, we are not describing a cage. We are describing a horizon, a frontier carved by light, a boundary defined by time, and beyond it, we don't know. We cannot know yet, but we can imagine. Maybe the universe repeats itself endlessly beyond our view. Clusters after clusters after clusters, like a cosmic ocean without shore. Or maybe it curls back on itself in ways subtle and cyclical, space folding like the surface of a sphere, too vast to perceive from within. Or perhaps the cosmos is infinite, truly infinite, in extent, meaning the part we see is not even a percent of a percent of a percent of what exists. And, well, these are not just philosophical indulgences. They are scientific possibilities grounded in measurements of cosmic microwave background radiation, in the geometry of spacetime, in the distribution of matter on the largest scales. But for now, for this chapter, it is enough to understand this. The observable universe is not a limit of space. It is a limit of light. And it tells us not what the universe is, but what the universe has allowed us to see so far. Which is why, as we go further, as we follow the outer edge of our cosmic bubble, the next question rises naturally from the darkness. If this horizon expands every year, why is it that we can never reach the true edge? Why do the galaxies near the boundary keep slipping away faster than light can chase them? That is the mystery waiting in the next chapter, where the expanding frontier of the visible universe becomes something stranger still, a horizon we can approach, but never touch. And, when we left the previous chapter, we found ourselves standing at the edge of something that isn't really an edge at all. A horizon, a moving frontier, a boundary defined not by what the universe is, but by how far light has traveled to meet us. And well, as strange as it already seems, the story grows stranger still once we notice a quiet paradox. This boundary is expanding every moment we exist, yet we will never reach it, never touch it, never see beyond it. It feels almost like chasing the horizon across an endless sea. No matter how fast you sail, the line where sky meets water retreats with equal grace. And that, Metzim, that, is exactly what the cosmic horizon does. It recedes, it expands, it stays always out of reach. So, let us step slowly into that paradox. Let us breathe with it. The observable universe grows by roughly 1 light-year in radius every year. Every moment we live, the sphere of space-time we can see becomes a little larger, a little wider, a little deeper. New galaxies drift into visibility, not because they moved toward us, but because their ancient light finally completed the long journey across expanding space. The the image is almost tender. Photons that have been traveling since the universe was young, finally brushing against our detectors like messengers delayed by the stretching road beneath them. But, well, if that is true, if we can see farther every year, then why do we say there is a limit? Why do we claim there are regions of the universe we will never see, no matter how long we wait? The answer lies in the accelerating expansion of the cosmos. You see, it's not just that space expands. Space expands faster and faster as time moves on. This accelerated expansion, driven by what we call dark energy, this invisible pressure woven into the very fabric of space-time, pushes galaxies away from us at increasing speeds. The farther away they are, the faster they recede. And, well, beyond a certain distance, the recession speed becomes greater than the speed of light. Not because galaxies are moving through space faster than light. No law is broken. But because space itself is stretching so rapidly that even a photon sprinting at the universal speed limit cannot bridge the gap. So, yes, the observable universe expands. But the unreachable region expands even faster. It's not a race between us and the galaxies. It's a race between light and the expansion of spacetime. And spacetime is winning. This leads to the quietly heartbreaking truth that defines the boundary of our cosmic understanding. There exist galaxies whose light will never reach us. Not now. Not in 10 billion years. Not even in 1 trillion years. They are part of the universe, but forever beyond our view. They sit behind a curtain that is not physical, but temporal. We call this boundary the cosmic event horizon. Not the edge of existence, not the edge of matter, just the edge of what light can ever communicate. And, the event horizon is smaller than the observable universe. Much smaller. This means there are galaxies we can see today, galaxies whose ancient light is only now arriving, that have already crossed into the unreachable zone. They shine into our telescopes from a past they no longer occupy. Their modern selves are lost behind the boundary. It feels almost nostalgic, as if we are watching a home movie of someone who has grown old or moved away, while the version we see remains young forever. And, well, this reveals something beautiful and sad at once. The universe we observe is a museum of light, not a map of what exists now. So, even though the observable region grows, the event horizon ensures we can never catch up with the present universe. It ensures that expansion, not light, defines the ultimate limits of cosmic knowledge. But there is another layer to this, a layer that shifts the way we imagine the universe itself. Because the horizon we see is not symmetrical in time. The observable universe expands outward faster than we age. Every year, new shells of ancient reality become visible. Every year, photons that once traveled through regions too distant for us to observe drift into reach. And yet, paradoxically, most galaxies move beyond our future reach long before their light arrives here. It's not a simple boundary. It's a moving, breathing, living boundary. It grows even as it retreats. And, this raises a profound question. What does it mean to live inside a universe whose visible frontier constantly expands, but whose accessible frontier constantly contracts? Perhaps, the universe is telling us something about the nature of perspective, that what we see is always a compromise between distance and time. That observation is always a negotiation between where something was and where it is now, and that the further we gaze, the more we are taught about the fragile relationship between seeing and understanding. We think of exploration as a matter of distance, but in the cosmos, exploration is a matter of time. So, the cosmic horizon is not just a boundary. It is a lesson, a reminder that the universe is not merely expanding outward, it is expanding away from us. Consider this. Every second, new space forms between us and distant galaxies. Every second, this new space adds to the total journey light must travel to reach us. So even though light races toward us at its maximum speed, the road ahead stretches beneath it like a treadmill accelerating upward. And, well, in many cases, the road stretches too fast. The finish line accelerates away, and the photon never arrives. It's not that the light slows. It's that the destination flees. And this concept, so counterintuitive to human intuition, trained by landscapes that do not grow, forms the quiet backbone of modern cosmology. It explains why we see galaxies from the first billion years, but cannot see galaxies forming today in the same regions of space. Their present-day light can never reach us. Their information is sealed away by space-time itself. And this brings us to one of the most poetic ideas in astrophysics. The universe grows faster than knowledge. Every year, our instruments improve. Every year, our telescopes reach deeper. Every year, our detectors become more sensitive. And yet, every year, more of the universe slips permanently beyond our reach. It's not just, but also, a reminder of the delicate balance between discovery and loss. The cosmos opens itself and closes itself at the same time. And, if we lean into this paradox rather than resist it, something beautiful emerges. A recognition that what we see is always incomplete, always curated by the physics of expansion. That our cosmic picture is not a photograph, but a story told by light with missing chapters, skipped pages, and entire volumes sealed behind a horizon we can never cross. So, why does this matter? Why dwell on horizons we can never reach? Well, perhaps because understanding the boundary helps us understand the nature of the universe beyond it. The cosmic event horizon tells us that the universe is not simply large. It is structured in a way that guarantees partial knowledge. It ensures that mystery is not an accident of our technology, but a fundamental property of spacetime. And, well, this mystery isn't a void. It's an invitation. A quiet hum beneath the equations, encouraging us to wonder, to imagine, to reach even when we know we cannot touch. This is where the philosophy of cosmology becomes inseparable from its science. Because when we contemplate the cosmic horizon, we are really contemplating our place in time. We are acknowledging that we are limited not by where we stand, but by when we stand. If we lived in the far future, the observable universe would look different. Larger. But the event horizon would have shrunk even further, locking more of the cosmos behind its accelerating veil. If we lived closer to the Big Bang, the horizon would be smaller, but the event horizon would be larger. That balance shifts with every cosmic moment. The universe is not static. Its visibility is not fixed. Its knowability evolves. So, we are lucky to exist now, in an era where the early universe is still visible, but the far future is not yet entirely sealed away. And, this brings us to a soft, lingering question, one that emerges naturally as we stare at an expanding horizon we can never touch. If the universe reveals itself only partially, only gradually, only in slivers of ancient light, then what lies beyond our horizon? What structures? What galaxies? What physics? And that, Well, that is the path opening before us in the next chapter, where we step beyond the boundaries of what we can see and begin to imagine the scale of what must exist beyond the cosmic curtain. And, when we left the last chapter, we found ourselves standing before that vast cosmic curtain, the horizon we cannot cross, the boundary that divides what light has shown us from what the universe refuses, at least for now, to reveal. And, well, as we press our hands gently against that invisible frontier, another question rises naturally, almost shyly. What lies inside this horizon we can see? How much of the universe has actually unveiled itself to our small and curious species? You see, for most of our history, the answer felt reassuringly small. For centuries, we thought the Milky Way was everything. One galaxy, one island universe, all stars bound to a single shining arch. But that illusion dissolved as soon as we pointed our first serious telescopes into the deep dark. And, well, since then, the numbers have grown with every new instrument we've built. Not gently, not steadily, but explosively, almost embarrassingly, as if the cosmos keeps laughing quietly at our attempts to measure it. So, let us begin with the first great revolution of scale. In the 1920s, Edwin Hubble looked at fuzzy patches of light, small, dim, ghost-like, and realized they were not clouds in our galaxy, but entire galaxies themselves, millions of light years adrift. And that changed everything. It broke the illusion that the Milky Way was the universe. It broke the idea that our cosmic home was unique. It showed us that we live in a vast archipelago of galaxies scattered across unimaginable distances. But even Hubble's discovery was only the first ripple. Because, well, when Hubble measured the number of galaxies in the visible sky, he reached into a darkness filled with structure that would remain hidden for nearly a century. His instruments could only glimpse the brightest galaxies, the closest islands, the great cosmic continents, the deep clusters, the faint spirals. Those would remain silent until our eyes grew sharper. Then came the Hubble Space Telescope, the modern one, not the astronomer, and its deep field experiment, one of the most daring acts in the history of science. Point a telescope at a patch of darkness, a region of sky so empty that no stars or galaxies were known to exist, and stare. Stare for days, letting light drip into the detector photon by photon. And, well, the result was astonishing. Thousands of galaxies bloomed out of the void. Spirals, ellipticals, compact dwarfs, ancient structures stretching back billions of years. A garden of light blooming in a place we thought was barren. So, the number of known galaxies leapt from billions to hundreds of billions. But even that wasn't the end. The ultra-deep field went deeper still, and the extreme deep field, 10 years of accumulated exposure, pushed the cosmic curtain back further. From this, astronomers estimated that the observable universe might contain 2 trillion galaxies. 2 trillion. The moment one says it aloud, it feels unreal. Trillion is a word of such magnitude that it slips through the fingers like sand. We cannot hold it. We can barely conceptualize it. But even 2 trillion was not the final word. Because, well, when James Webb unfurled its golden mirrors and began to peer into the deep infrared, the wavelengths that stretch through cosmic dust and ancient space, another surprise emerged. The earliest galaxies, the faintest structures, the tiny seeds of cosmic formation, were far more numerous than we expected. Webb did not simply add galaxies to our catalog, it multiplied them. Imagine this. For every galaxy we saw in visible light, there might be 10 more hidden in wavelengths the human eye can never perceive. Galaxies too distant, too redshifted, too faint for Hubble to ever glimpse. Webb's first surveys revealed countless tiny smudges, galaxies from the universe's first few 100 million years, so abundant that our previous estimates may have been low by a factor of 5. So, instead of 2 trillion galaxies, the observable universe might contain 10 trillion. 10 trillion islands of light scattered through a cosmic ocean we barely understand. It's not just more galaxies. It's more structure, more history, more complexity. The universe, it turns out, was busy early, far busier than we assumed. The first stars ignited quickly. The first galaxies assembled rapidly. The first clusters emerged like embers blowing into fire. And, if 10 trillion galaxies exist within our observable sphere, then think about the stars. Think about the multiplier effect. Each galaxy contains billions or trillions of stars. The numbers rise beyond arithmetic into poetry. 10 trillion galaxies. 100 billion stars per galaxy. 1 trillion stars across the sky. The scale is so immense that it collapses our intuition. It breaks something in the mind, gently, but irreversibly. The universe becomes less like a place and more like a principle, an argument for existence played out on a stage too vast for comprehension. But, well, perhaps what matters most is not the count, not the number, not the immensity itself. Perhaps what matters is the idea that every time we stare deeper, the universe grows. We thought the observable universe contained a few 100 billion galaxies, then 1 trillion, then 2, now perhaps 10. And still, we are only describing the galaxies whose light has had time to reach us. So, the most humbling truth is this. The number of galaxies we see is not the number that exist. It is the number the universe has allowed us to see so far. And, that's before we even consider the galaxies hidden behind dust, or behind the bright plane of the Milky Way, or behind epochs of cosmic fog where hydrogen clouds swallowed early starlight. When we account for those, if we could somehow clean the cosmic lens, our estimate might double again, or triple, or vanish into infinity. The early universe was not a sparse field of isolated sparks. It was crowded, teeming, bursting with star formation, bursting with structure, bursting with interactions that eventually carved the large-scale cosmic web. Every galaxy carries a memory of that era. Every cluster is a fossil of ancient gravity. Every faint smudge in the deep field is a message sent from a time when the universe was a fraction of its present size. And, well, even the idea that we can number these galaxies at all might be an illusion crafted by the limits of our perception. The very concept of how many begins to break in a universe where the volume we can see is not the volume that exists. So, perhaps the right way to think about the observable universe is not as a catalog but as a window, one frame of an infinite panorama, a fleeting moment captured by light that began its journey when the stars were young. Think of it like diving in the ocean. The surface above you glitters with sunlight. The water around you swirls with fish, corals, currents. It feels vast, endless. But you know, deep down, you're seeing only a thin slice, a fraction. Whisper. The ocean stretches far beyond your reach. The universe is the same. The cosmos is the same. The trillions of galaxies are the same. They are the visible fraction of a reality so immense that our words bend under its weight. And, as we contemplate these trillions of galaxies scattered across billions of light years, another question stirs within the quiet spaces of the mind. If this is what we can see, a fraction, a sliver, then what lies in the regions beyond sight? What cosmic continents stretch across the darkness we will never receive light from? What structures form in the regions forever hidden behind the event horizon? What threads of the cosmic web span distances too vast for photons to cross? We grow older, clocks tick, but light travels on. And yet, the universe outruns even that. And, well, that is where the next chapter leads us. From the visible immensity within our cosmic horizon to the unseen territories beyond it. Regions so vast, so unreachable, that even the boldest telescopes of the future will never glimpse them. The observable universe may hold trillions of galaxies, but the true universe, the one beyond the curtain, may be hundreds of times larger, or infinite, or something stranger still. And so, we turn now toward that possibility, toward the grander scales hinted at by cosmic geometry, by background radiation, and by the faint, ancient fingerprints written into the sky itself. And, as we stepped away from the dizzying revelation that even 10 trillion galaxies may represent only a fraction of what truly exists, another curtain began to rise. Not one stretched across the outer cosmos, but a nearer veil, quiet, familiar, and almost intimate in comparison. Because, well, before we dream too far beyond our observable horizon, perhaps we ought to pause and peer more closely into the shadows cast by our own cosmic home. You see, for all our grand telescopes and deep surveys, we have never truly observed the entire sky. Not completely, not evenly, not clearly. The Milky Way, magnificent as it is, stretches across our view like a luminous river, but beneath its shimmering band lies something less poetic, an obstruction, a shield, a mask, a great swath of dust and gas that hides nearly a fifth of the universe from our sight. And, well, this hidden region has earned a quiet but evocative name, the Zone of Avoidance. So, imagine standing behind a waterfall, light cascading down, beautiful, brilliant. Yet behind that curtain lies a world misted out of reach. The Milky Way does something similar. Its dense plain of stars, interstellar dust, molecular clouds, stellar nurseries, and ancient debris forms a luminous fog that blocks our view of whatever lies beyond its disk. Roughly 20% of the extragalactic sky resides behind this obstruction. 20% of the universe that should be visible, but isn't. And for decades, astronomers simply had no way to pierce it. The irony is gentle but striking. The galaxy that gives us our sense of belonging also blinds us. And, this blindness once led to surprising mysteries. In the 1970s and 80s, astronomers began noticing strange motions, galaxies drifting with unexpected speed, as if tugged by something massive, something gravitationally powerful, lurking in a direction we could barely see. This unseen pull became known as the Great Attractor. And, well, the Great Attractor was not small. Its gravitational influence extended across hundreds of millions of light years, drawing galaxies, including our own, toward a region smothered by the Milky Way's dust. So, for years we sensed something there, something enormous, shaping our motion across the cosmos, but we could not see it. It was as though gravity itself was pointing to a hidden continent while our eyes remained blind. We eventually uncovered parts of this structure with radio telescopes, which peer not through visible light, but wavelengths that slip through dust like whispers through curtains. Infrared surveys followed, lifting yet more of the veil. And, well, what they revealed was startling. Not a single monolithic structure, but a tapestry of clusters, filaments, and superclusters. Pieces of a vast gravitational basin pulling whole regions of space toward it. And that discovery reshaped our understanding of the local universe. It suggested that cosmic maps were incomplete, and that entire structures, immense structures, could hide in the Milky Way's shadow. But the great attractor was only the beginning. Deeper still, behind even more obscuring dust, lay another colossal feature, the South Pole Wall. A sprawling superstructure of galaxies stretching over 1 billion light-years across. We didn't know it existed until very recently, not because it was faint, but because it sat directly behind one of the thickest lanes of our galactic disk. And, this raises an uncomfortable but necessary truth. Even with modern instruments, the Milky Way still hides things from us. Every new radio or infrared survey reveals something previously concealed. Every improvement in sensitivity lifts another corner of the cosmic curtain. So, though we often speak of telescopes like Webb or Hubble as instruments that show us the universe, what they truly show is a curated portion of the universe. The parts not hidden behind dust, not drowned in glare, not lost behind gas or stars. And the zone of avoidance reminds us that the cosmos holds secrets right next door, not only at the edges of the observable realm. But perhaps the most intimate lesson of this hidden zone is not about what we can't see, but how we've learned to see differently. The invention of radio astronomy was not just a technological leap. It was a philosophical shift, a change in our relationship with light itself. Because, well, radio waves do not care about dust. They pass through it effortlessly. They reveal the skeleton of the galaxy, its hydrogen clouds, its cold gas, its spiral arms traced not by starlight, but by faint emissions at 21 centimeters. Infrared light, too, slices through dust like a warm knife. Instruments like the Spitzer telescope and now the James Webb Space Telescope can reveal stars and galaxies buried behind layers of cosmic fog. So, in a sense, we have learned to listen to the universe through multiple languages, not just the visible, not just the infrared, not just the radio, but the full symphony. And this diversity of perception has shown us something deeply humbling. The universe we see depends entirely on the wavelength with which we look. The Milky Way may block visible light, but in radio it becomes transparent. In infrared, it softens. In gamma rays, it glows fiercely. In X-rays, it reveals violent events the naked eye could never dream of. It's not that the universe hides itself. It's that each shadow is only a shadow in one type of light. And, well, that insight leads us to reconsider the meaning of observable. Because what is observable depends on how we observe. The dust lanes that erase galaxies in one wavelength become invisible in another. The darkness that conceals a supercluster becomes transparent in the radio. The zone of avoidance shrinks or expands depending on which part of the electromagnetic spectrum we choose to listen to. So, even the 20% of the sky we once thought inaccessible is not truly lost. It is simply coded differently. A different message written in a different ink. And yet, even with all these tools, even with the full spectrum at our disposal, there are still structures lurking behind the Milky Way that we have not fully mapped. Some are too faint, some too distant, some drowned by foreground stars, some blurred by gas clouds we cannot yet fully subtract from our data. The South Pole Wall, for instance, emerged only when astronomers used sophisticated reconstructions of galaxy motions, not direct imaging, to infer its presence. Gravity exposed what light could not. And, that realization is almost poetic. The universe speaks not only through what it shows, but through how it pulls. Sometimes gravity tells the truth before light does. And this duality, light revealing form, gravity revealing structure, will guide the next generation of cosmic cartography. As we push deeper into the obscured regions of the Milky Way's shadow, our tools will shift once again. More sensitive infrared arrays, more powerful radio interferometers, gravitational wave detectors mapping collisions in hidden corners of the sky. We grow older, clocks tick, and our view of this cosmos becomes sharper, not because the universe changes, but because we do. So. The zone of avoidance is not merely an obstacle. It is a reminder of our limitations, a reminder that every map carries blind spots, a reminder that knowledge is always partial, always growing, always emerging from the shadows. And well, as we contemplate this, another question surfaces quietly from beneath the dust. If our own galaxy hides entire superstructures, what about the cosmic web itself? What shapes lie just beyond the veil? Shapes so large they defy our theoretical expectations, structures that challenge the very models we use to understand cosmic evolution. That is where the next chapter leads us. Toward the giants of structure, the filaments and walls so vast, so improbable, that they force us once again to rethink the universe not as a static map, but as a living story unfolding across billions of years. And, as we drift away from the Milky Way's veil, from that curtain of dust and starlight that so elegantly hides vast structures behind it, we begin to sense something even stranger emerging from the cosmic dark. Because, well, if entire superclusters can hide behind our own galaxy, then what else might be hiding far beyond it? What shapes, what giants, what improbable architectures could be waiting in the deeper cosmic web? Structures so large, so sprawling, that they challenge not just our instruments, but our theories themselves. This is where the universe reveals another layer of contradiction. We assume that as we push deeper into the cosmos, our models of structure formation will guide us safely through the unknown. Lambda CDM, the elegant marriage of cold dark matter and dark energy, has been our compass for decades. And that model does predict the formation of large-scale structure, filaments, walls, nodes, and voids, forming a cosmic web stretching across billions of light years. So, it wasn't surprising when astronomers uncovered massive walls like the Sloan Great Wall or the Hercules Corona Borealis Great Wall. These structures were vast, yes, but just within the upper limits of what the model could allow. But then something unusual surfaced. A structure so large, so elongated, so utterly unexpected that it forced cosmologists to pause. A structure called the Giant Arc, bending across 3 billion light-years. And, well, just as we absorbed that discovery, another appeared. Longer, stranger, more intricate. A cosmic object named the Big Ring, spanning more than 1 billion light-years. And then, came the Kipu, a superstructure stretching around 1.4 billion light-years, curling through space like a cosmic knot woven by the universe itself. The name Quipu comes from the ancient Andean recording system. Strings knotted to encode information. A surprisingly poetic metaphor, because the universe here seems to be tying its own knots, leaving signs etched into its structure as if it were recording its own history. So, why do these structures matter? Why do they make cosmologists uncomfortable? Well, because they challenge the statistical expectations of lambda CDM. Our current model predicts that cosmic structures should not exceed a certain scale, that the universe should be homogeneous on large enough distances, that randomness should dominate, that patterns should dissolve. But these giants, these knots, these arcs, these rings, seem to hint at something else, some coherence, some persistence, some organization on scales larger than we anticipated. It's not that the model is wrong. It's that the model may be incomplete. These structures do not break physics, but they do stretch it, like edges of a canvas pulling against the frame. The cosmic web forms through a delicate dance of dark matter, expansion, and the primordial density fluctuations seeded in the earliest moments of existence. But when a structure stretches more than 1 billion light-years across, we must ask, were those early fluctuations more intense than we thought? Was dark matter more clumpy? Was inflation not just fast, but uneven? Did the universe leave imprints from a physics that predates the Big Bang itself? And, well, these questions linger not because we don't have answers, but because the universe invites us to ask them. Yeah. The Quipu in particular is unsettling in its elegance. A long, thin, knotted segment of galaxies that shouldn't be arranged in such a clear pattern. The probability of such a structure forming by random chance is low. Not impossible, but uncomfortable. It prompts the slight tightening of brows in conferences, the quiet murmur in seminar rooms, the soft click of pens as cosmologists redraw diagrams. And, when a model begins to stretch in this way, theory and observation begin a new conversation. One says, "Explain me." The other whispers, "I will try." But in that space between whisper and explanation, science grows. So, what could cause these giants? Perhaps regions rich in dark matter, forming massive gravitational highways. Perhaps anisotropies left behind by inflation's early quantum ripples. Perhaps we are witnessing rare statistical outliers, flukes in a universe large enough to make improbabilities almost inevitable. It's not that the universe contradicts us. It's that the universe challenges us to think bigger. And the more we look, the more we find. Structures like the huge large quasar group, a cluster of quasars spanning 4 billion light-years, or the Great Wall itself, a 1.5 billion light-year chain of galaxies, or the Horologium supercluster, or the Shapley concentration. Each discovery is a reminder that the universe arranges itself into patterns we never would have predicted if we relied solely on equations. And, well, here lies the quiet beauty of cosmology. The mathematical universe and the observed universe meet, sometimes shaking hands, sometimes debating, but always revealing more of themselves. Imagine standing at the base of a mountain range you believed stretched only 100 kilometers, only to discover that it runs 1,000, then 2,000, then crosses continents. That is the feeling these superstructures evoke. The cosmic web is not a gentle mesh. It is an architecture, bold, intricate, sprawling. It is the universe's handwriting, and the Quipu, the big ring, the giant arc. They are sentences in a language we are only beginning to decipher. So, What do these structures teach us about the cosmos? First, they tell us that dark matter is the scaffolding upon which everything hangs. Without it, these giants could not form. Their gravity would fall apart. Their filaments would unravel. Their clusters would drift. Second, they tell us that the early universe contained fluctuations of density, tiny wrinkles in space-time, that grew into the cosmic web. But these wrinkles may have been more pronounced, more complex, more structured than we assumed. And third, they whisper that cosmic evolution is not smooth. It is not gentle. It is turbulent, chaotic, and carved by processes that push our theories toward their edges. When we step back, when we zoom out far beyond any galaxy, any cluster, any void, we begin to see the universe as a vast, interconnected embroidery. Filaments stretching for hundreds of millions of light years. Clusters anchoring their centers. Walls forming boundaries. And voids providing the dark contrast against which the luminous patterns emerge. And, well, in that embroidery, these superstructures are the boldest strokes. It's not out there. It's in here, in the equations we write, in the models we refine, in the wonder we feel when the universe confronts us with something so enormous that the mind strains to hold it. We grow older. Clocks tick. And yet the universe keeps revealing giants older than time can fully express. But perhaps the real significance of these structures lies not in their scale, but in what they imply about what lies beyond them. Because if structures this big exist within our observable bubble, just a fraction of the whole, what unimaginable giants might dwell beyond our sight? What cosmic continents stretch across the unseen universe, dwarfing even the largest we have found? And, that question leads us naturally, almost inevitably, toward the next domain of cosmic discovery. The voids. The vast, dark regions the size of hundreds of millions of light years where almost nothing exists at all. Because, well, the universe is not only a story of presence, it is a story of absence, of emptiness sculpting the form of everything that fills it. And well, the next chapter invites us into that darkness, to wander the great cosmic voids that sit like oceans between the luminous continents of the universe. And, as we drift away from those luminous giants of the cosmic web, from the arcs and rings and tangled knots of galaxies stretching across billions of light years, something quieter begins to emerge. Well, you see, if the universe writes its story in bright strokes of starlight, it also leaves vast blank pages between each chapter, pages so empty, so gentle in their darkness, that they almost feel like pauses in the universe's breath. These are the voids. Not voids in the poetic sense, not the metaphors we whisper to ourselves in lonely moments, but actual cosmic regions, hundreds of millions of light years wide, containing almost nothing at all. And, well, the strangest thing is that these voids are not exceptions. They are not cosmic mistakes. They are part of the pattern, a necessary counterpoint to the superstructures we just explored. So, imagine the universe as a great sponge, its filaments forming the solid edges while the voids fill nearly all the space in between. Most of the cosmos is not galaxies or stars or gas. Most of it is silence. Among these voids, some are legendary. Some feel almost mythic in scale. The Boötes void, for instance, a region nearly 300 million light-years across with only a handful of galaxies scattered through it, like lonely lanterns in a cavern. And then the giant void, even larger, stretching nearly 1 billion light years. These are spaces so large, so achingly empty, that when astronomers first mapped them, they wondered whether the universe had somehow torn or whether our instruments were failing. That is how unprepared we were for such vastness. And, yet they are real. They are carved not by accident, but by the physics of the early universe. You see, well, everything begins with the primordial density field, the tiny wrinkles in space-time imprinted in the cosmic microwave background. Regions slightly denser than average would collapse, forming galaxies, clusters, filaments. Regions slightly less dense would expand faster, pushing matter away, becoming emptier and emptier over billions of years. So, voids are not holes. They are consequences, natural outcomes of a universe seeded with randomness and shaped by gravity. They are the shadows cast by structure. When you look at a void, you're not seeing the universe failing to form something. You're seeing the universe succeeding in sculpting contrast. And, well, perhaps that is why voids feel so strangely beautiful. They give form to the cosmic web by being absent from it. They remind us that structure needs emptiness, that creation requires space. But the scientific significance of voids goes far deeper, because, well, voids are laboratories. Quiet, uncluttered regions where the subtle influence of dark matter can be studied without interference. In dense regions, clusters, walls, filaments, gravity becomes chaotic, nonlinear, tangled. But in voids, everything is clean. Gravity behaves gently, linearly. It becomes measurable. That makes voids precious to cosmologists. By measuring how galaxies drift around the edges of voids, we can infer the density of dark matter. By studying how voids expand, we can probe the influence of dark energy. By mapping their shape, we can test whether space-time bends exactly as Einstein predicted. It's not that voids are empty. It's that voids are honest. They reveal what matter-filled regions often hide. The Bode's void, for instance, expands slightly faster than the denser surroundings because dark energy dominates more completely in emptier regions. That difference, small as it is, helps refine our understanding of the accelerating universe. And the giant void, where galaxies on its outskirts move in ways that hint at irregular dark matter distribution, may hold clues to new physics, or simply to statistical quirks in the primordial fluctuations. So, the emptiest places may be the most informative. And yet, there is another layer to this story, because voids are not uniform emptiness. They carry faint traces, ghost structures, nearly invisible filaments, low-density galaxies drifting like forgotten islands. These galaxies often behave strangely. Some show rapid star formation despite lacking nearby companions. Some form stars sluggishly, as though starved of material. Some display odd rotations, influenced by dark matter halos more massive than expected. And, it is in these anomalies that cosmologists search for clues. Perhaps these whisper-small galaxies remember something about the early universe that brighter, denser galaxies have forgotten. Perhaps their relative isolation preserves ancient signatures, unaltered, unperturbed, untouched by the violent mergers that reshape galaxies in denser regions. In that sense, voids may hold some of the purest fossils of cosmic history. The notion is quiet but profound. The universe hides its oldest relics not in the crowded, luminous cities of galaxies, but in the silent countryside of space. And, well, thinking about this makes me pause, because when we picture the cosmos, we picture light, nebulae, spirals, exploding stars. We picture the bright things, but the universe is mostly dark, mostly space, mostly nothing. It's not out there. It's in here, in the way we imagine the universe as an exhibition of light rather than a tapestry of contrast. We grow older, clocks tick, and only slowly do we realize that darkness shapes the cosmos just as profoundly as light. But voids offer yet another mystery, a puzzle that has nudged at cosmology for decades: the cold spot. A region of the cosmic microwave background that appears significantly cooler than expected, so large and so distinct that some have suggested it may be the imprint of a supervoid, or perhaps something stranger. And, while surveys have identified a massive void in that region, the El Gordo supervoid, its size may not fully explain the cold spot's intensity. Some propose exotic physics. Others suggest statistical fluke. Others imagine interactions between our universe and something beyond it. So, voids might not only be products of the cosmic web, they may be signatures of deeper cosmological processes we have yet to understand. And as radio telescopes grow more sensitive, as deep surveys map galaxy motions with greater precision, voids may become key tools for measuring neutrino masses, probing modified gravity, or refining dark energy models. The emptiness, ironically, contains the clues. And, that brings us to the human side of this, because contemplating voids, true voids, forces us to reckon with scales so enormous, so hollow, that our minds push back. We are creatures of boundaries, of walls, rooms, horizons, familiar shapes. The idea of a billion light-year emptiness unsettles us. But maybe that discomfort is good. Maybe it reminds us that the universe is not tuned to human intuition. When we look into a void, we are staring not at absence, but at possibility, at the untouched canvas of the cosmos, at the regions where the universe allows itself to breathe. And the more we learn about voids, the more they push us towards the next fundamental truth, that everything we see, every star, every galaxy, every cluster, is only a tiny fraction of what exists. The bright parts, the easy parts, the parts drawn in light. The rest, the rest is invisible. Dark matter sculpting the web. Dark energy accelerating the expansion. Forces we cannot touch or see, yet undeniably real. And, as the great voids lead us gently into this realm of the unseen, the next chapter of our journey must turn toward those invisible substances themselves. To the matter we cannot detect with light, and the energy that pushes galaxies apart. Because the emptiness of the universe is only the beginning. The true mystery lies in the darkness that fills even the brightest places. And, as we leave behind the vast quiet of the cosmic voids, that gentle darkness where the universe seems to breathe between its structures, we step into a stranger realm, one where what we see becomes almost irrelevant. Because, as we've learned again and again, the universe hides most of itself. It is not simply dark. It is deeply, profoundly invisible. And yet, everything that is invisible shapes everything that we see. This is where our journey becomes both unsettling and beautiful. Because if the voids taught us about emptiness, now, we must confront the truth of what fills that emptiness. Matter that does not shine, energy that does not glow, forces that do not announce themselves except through their effects. That is the story of dark matter and dark energy. And, the astonishing part is that these invisible ingredients make up 95% of the universe. Everything we know, stars, planets, galaxies, atoms, everything familiar, everything luminous, is only 5% of reality. 5% is us. 5% is home. 95% is mystery. So, let us begin with dark matter, the unseen scaffolding of the cosmos. The story starts in the 1930s, when astronomers studying galaxy clusters noticed something impossible. The galaxies inside these clusters were moving too fast. Gravity from the visible matter, stars, gas, planets, was not enough to hold them together. By every calculation, the clusters should have flown apart. And, yet they hadn't. It's not that our measurements were wrong. It's not that Newton suddenly failed. It's that something was missing. Well, this is where the idea of dark matter quietly entered the scene. A kind of matter that exerts gravity but does not emit light, does not absorb light, does not reflect light. Matter that interacts with the universe only through gravity. Decades later, Vera Rubin confirmed this mystery on a galactic scale. She measured the rotation curves of spiral galaxies and found that stars far from the center were moving far faster than expected. According to classical mechanics, the outer stars should slow down. They didn't. They moved as if each galaxy were embedded in a massive, invisible halo. That was the evidence no one could ignore. So, dark matter became the silent architect of cosmic structure. Without it, galaxies would tear themselves apart. Without it, the cosmic web would collapse. Without it, there would be no clusters, no filaments, no walls, no vast structures that stretch across billions of light years. The bullet cluster later provided one of the most elegant demonstrations. Two galaxy clusters collided, and the hot gas, visible in X-rays, slowed down while the gravitational mass, mapped through gravitational lensing, passed straight through. The visible matter lagged, the invisible matter led. It's not just a theory, it's a measurement, a weighing of the invisible. And, gravitational lensing has become our most powerful tool. When light bends around massive objects, it reveals the distribution of dark matter as if the universe were pressing its fingerprints into space-time. So, we know dark matter is real. We know its mass. We know how it moves. We know how it shapes the universe. But we do not know what it is. Not protons or neutrons or electrons. Not dust. Not gas. Not black holes. Not anything in the standard model of particle physics. It is something else. A new form of matter. A new ingredient of existence. And that is humbling. Well, in a universe that glows with stars and galaxies, the true architecture is drawn in darkness. But dark matter is only the beginning. Because in 1998, astronomers studying distant supernovae discovered something even stranger. The universe was not slowing down as gravity pulled galaxies together. It was speeding up. Expansion was accelerating. That was shocking. Utterly unexpected. Theoretical heresy. And, the only explanation consistent with Einstein's equations was a form of energy inherent to space itself. Dark energy. If dark matter pulls, dark energy pushes. If dark matter binds structures, dark energy stretches them. They are cosmic opposites, dancing across the universe. Dark energy now makes up nearly 70% of the universe. More than all matter combined. More than dark matter. It is the dominant force shaping the fate of the cosmos. So, what is it? We don't know. It might be the cosmological constant, Einstein's mathematical term reinterpreted as a physical property. It might be the energy of the vacuum itself, quantum fluctuations woven into space-time. It might be something dynamic, changing over time, shifting the destiny of the universe in ways we have not yet imagined. And, well, these possibilities are not hand-waving. Dark energy is measured, quantified, observed. Its fingerprints are carved into supernova brightness, galaxy distributions, baryon acoustic oscillations, and the cosmic microwave background. It's not a placeholder. It's not speculation. It's real, and it's accelerating everything. And this raises a profound philosophical question. If 95% of the universe is invisible, unknowable through direct detection, then what does it really mean to see the universe at all? When we talk about the observable cosmos, we speak as though light is the ultimate arbiter of reality. But light is only one messenger. Gravity is another. Structure is another. Expansion is another. Our senses evolved to witness a world made of atoms, but the universe is built from forces and fields far stranger than our perceptions. Well, perhaps this is where humility returns. Perhaps this is where wonder expands. Because you see, the darkness is not empty. The darkness is full of matter that holds galaxies together, full of energy that tears space apart, full of phenomena woven into the universe so deeply that without them, nothing recognizable would exist. And yet, the invisibility of dark matter and dark energy also sets the stage for one of the most poetic truths in cosmology. We can understand what we cannot see. We can measure what escapes our eyes. We can map what offers no light. The universe may hide itself, but it leaves clues everywhere. And, well, this ability, this astonishing power to read the unseen from the seen, is what allows us to move forward into the next great challenge, stitching together all wavelengths, all messengers, all instruments into a single coherent picture. Because our telescopes only capture fragments of reality. The rest must be assembled like a cosmic mosaic. Radio waves reveal hydrogen stretching across the early universe. Infrared lets us see galaxies shrouded in dust. X-rays expose the violent hearts of clusters. Gamma rays trace the universe's most extreme events. Gravitational waves whisper of collisions in total darkness. It's not one universe. It's many layers of the same universe. And the darkness, paradoxically, becomes the glue between them. But before we move into that next mosaic, into the world where multi-wavelength astronomy reveals layers of reality far beyond our eyes, let us pause for a moment. Let us reflect. We grow older, clocks tick, and we begin to understand that the visible cosmos, the galaxies, the stars, the glowing nebulae, is only the froth on an ocean of deep, dark physics. The universe is not just large, it is subtle, it is hidden, it is waiting. And, the next step of our journey leads exactly there, to the limits of our instruments, to the challenges of seeing a universe that prefers to remain unseen, to the question of why even our most powerful telescopes have surveyed only a tiny fraction of the deep sky. So, well, let us walk onward, from the mysteries of the invisible into the mysteries of the barely seen. And, as we step gently away from the realm of the invisible, dark matter shaping structure in silence, dark energy stretching the universe with its quiet insistence, we arrive at an even more humbling truth. Well, for all our telescopes, for all our ingenuity, For all the mirrors we polish and the detectors we cool to near absolute zero, we have only skimmed the surface of the deep sky. You see, when people imagine astronomy today, they picture spacecraft orbiting far above the Earth, instruments like Webb unfolding their golden mirrors, or sprawling observatories scanning the heavens. And that gives the impression that we have surveyed the universe comprehensively, that the cosmos has been mapped like a globe. But the truth is softer, quieter, and more astonishing. We have seen only a tiny fraction, not 10%, not 1%, but about 1/10 of the deep sky. And, well, the reason is surprisingly simple. Every telescope faces a trade-off, a choice between looking wide or looking deep. So, imagine standing at the edge of an ocean with a flashlight. You can sweep the beam across the entire horizon, broad, fast, shallow. Or you can shine it into a single patch of water, narrow, slow, deep. But you cannot do both at once. Telescopes work the same way. The Hubble Space Telescope gave us the famous Deep Field, an image so profound that it revealed thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. It changed astronomy. It changed the story of the universe. It showed us that the night sky, what looks empty, is overflowing with galaxies. But well, that image covered only a tiny pinprick of the sky, a fraction so minuscule that if you tiled the entire celestial sphere with fields of equal depth, you would need millions of them. So, even after decades, Hubble surveyed only a sliver. And then came Webb, with its golden hexagons and its ability to see the earliest galaxies glowing in infrared light. Webb can see deeper than Hubble, farther back in time, through more dust, into more ancient epochs. But deeper means slower. Slower means narrower. And narrower means less of the sky. And, well, Webb is not a sky surveying machine. It is a scalpel, not a net. It can stare into the deep universe and reveal galaxies from the first few 100 million years after the Big Bang, but it cannot map the cosmos broadly enough to find all the rare structures that lie scattered across the universe. It's not that technology is lacking. It's that physics demands compromise, wide but shallow, or narrow but deep. Never both. Consider this. To observe the entire sky with the depth of the Hubble Ultra Deep Field would take hundreds of thousands of years of exposure time. Not figuratively, literally. Even surveying 1% of the sky that deeply would occupy the entire lifespan of multiple telescopes, and Webb's deep fields would take even longer. So, when we say we have observed only 0.1% of the deep sky, that is not an exaggeration. It is a generous estimate. The vast majority of the cosmos lies unexamined, unphotographed, unexplored, and, that means something crucial. Everything we know about the deep universe is based on samples. Tiny samples. Well, imagine trying to understand Earth by looking at 1 square kilometer of land. Perhaps you see forest, perhaps desert, perhaps mountains. Whatever you see, you might assume the whole planet is similar, but you would be wrong. The universe is the same. Our deep fields are tiny windows, and beyond those windows lies terrain we have barely touched. This is why cosmic structures, giant arcs, Huipu-like filaments, massive superclusters surprise us. We stumble upon them almost accidentally in the tiny regions we examine. What else lies in the darkness? What if the universe contains structures stranger and larger than any we've yet seen? but located in the 99.9% of sky we have not mapped deeply. And, well, the same challenge applies to the most ancient galaxies. Webb has revealed galaxies that formed far earlier than models predicted. Too bright, too massive, too grown up for their cosmic age. Are these galaxies common? Are they rare? Are they statistical flukes? Or are they the norm in regions we have not yet observed? We don't know. We can't know. Not yet. So, once again, the universe reminds us to be humble. Every time we peer deeper, the cosmos becomes more surprising, not less. And yet, this limitation, this inability to survey the entire sky at great depth, does not diminish our knowledge. It shapes it. It encourages us to build mosaics, to stitch together broad surveys with deep exposures, to combine fast telescopes with slow ones, to use machines like the Vera Rubin Observatory for wide field speed, and machines like Webb for microscopic depth. It's not one telescope that reveals the universe. It's the conversation between them. And, perhaps this is the deeper message. The universe cannot be captured all at once. It must be gathered in layers, wavelengths, exposures, epochs. Like studying a painting not by looking at the whole canvas, but by examining fragments, tiny squares of color, then trusting that one day they will assemble themselves into something coherent. This limitation also carries a kind of beauty, because if we had already mapped everything, if the sky were fully cataloged, if every galaxy were known, we would lose something precious. Mystery. The fact that 99.9% of the deep sky remains untouched means that discovery is not slowing down. It is accelerating. Each new instrument, each new survey, each new wavelength uncovers something unexpected. The universe is not yielding its secrets. It is offering them slowly. And, well, this brings us to the next great veil. The fact that even when we do observe the sky, even when we stare into the deepest darkness, we still see only part of the story. Because every wavelength shows a different universe. Radio reveals hydrogen stretching across cosmic filaments. Infrared uncovers galaxies shrouded in dust. X-rays point to the hot, violent hearts of clusters. Gamma rays show cosmic explosions far beyond anything our eyes could bear to witness. Each wavelength opens a new sky, a new cosmos, a new truth. So, as we leave behind the limitations of deep surveys, our path leads naturally toward that idea, toward the multi-wavelength universe, where reality reveals itself not in one color, but in many. And, well, that is where we go next, toward the notion that the universe is not a single image, but a layered symphony waiting to be heard. And, as we drift from the question of how little of the deep sky we have truly surveyed, there's a quiet realization that settles in, perhaps gently, perhaps with a kind of cosmic weight. It's that even when our telescopes do look outward, even when they stare for days into one tiny grain of the heavens, they still do not show us the universe as it really is. Because, well, what we call seeing is itself a narrow act of translation. We see in one wavelength. The cosmos sings in many. You see, our eyes evolved on a small rocky world lit by a small yellow star. Our senses are tuned to a narrow band of electromagnetic radiation, a thin sliver we call visible light. But the universe is not made of visible light. It is not shaped by it. It is not limited by it. It's not just the stars glowing in optical wavelengths. It's not just the galaxies painting soft spirals across the dark. It's not out there. It's in here, this limitation in our biology. So, astronomy had to become something else. It had to become multi-wavelength, a form of listening rather than looking, a way of reading a universe written in frequencies beyond our senses. And, well, this is where the sky begins to fracture beautifully into layers. Radio reveals a universe of structure and motion. Infrared uncovers a universe of dust and ancient light. X-rays unveil violence. Gamma rays reveal the extremes. And each wavelength gives us a completely different cosmos. Let's begin gently with radio. Well, radio astronomy shows us hydrogen, the most abundant element in the universe, stretching like ghostly threads between galaxies. When we tune our instruments to the 21-centimeter line, we see the cosmic web more clearly than any image of stars could ever show it. We see jets fired from supermassive black holes, colossal beams of plasma acting like cosmic lighthouses, shining not in light we can see, but in radio waves that whisper across billions of light years. That, that, already tells us something profound. The visible universe is only the decoration. The true structure is hidden in frequencies we cannot sense. And, infrared pushes us even further. Infrared light slips through dust that blocks visible light. It reveals stellar nurseries, young galaxies, and the early universe softened by distance and time. This is why Webb, with its golden eye tuned to infrared, can see the first galaxies forming, a universe not yet mature, not yet arranged into grand spirals. It's not that these galaxies were invisible before. It's that we were looking with the wrong eyes. Then there is X-ray astronomy, the domain of the hot and the violent. Colliding galaxy clusters glow not in visible light, but in X-rays, because their gas is heated to tens of millions of degrees. Black holes, though themselves dark, announce their presence through X-ray flares as matter spirals in. Entire clusters of galaxies reveal their mass distribution through the shape of their X-ray halos. So, X-rays give us a universe of heat and pressure. And gamma rays, well, they give us the universe at its most extreme. Gamma rays are the signature of cosmic catastrophes, the collapse of massive stars, the collision of neutron stars, the birth of black holes, jets moving at nearly the speed of light. These events shine brighter than entire galaxies for mere seconds. In gamma rays, we see the rarest, most violent pages of the cosmic story. And when you place all these layers together, something extraordinary happens. The universe becomes whole. It's not just a matter of adding more colors. It's a matter of adding more dimensions. The cosmic web in radio, the early galaxies in infrared, the hot clusters in X-rays, the explosive events in gamma rays. And, well, this layering is not optional. It is essential. Because if you observed the Virgo cluster only in visible light, you would see galaxies calmly orbiting one another. But in X-rays, you would see a vast sea of hot plasma binding them together. And in radio, you would see jets from black holes shaping the environment. 3 universes, overlaid on one cluster. So, what is the real Virgo cluster? Which one is the true universe? All of them. And this is the deeper truth. There is no single universe we can observe. There is no single wavelength that reveals reality. Each wavelength slices through the cosmos like a knife through layered stone, exposing a new geological era of physics. We grow older, clocks tick, and with every new telescope, every new frequency, every new detector, the universe expands not outward, but inward. revealing its hidden architecture. Well, perhaps the most poetic example is the cosmic microwave background, the oldest light we can ever see. Not visible, not ultraviolet, not infrared, but microwaves, the afterglow of the Big Bang. A soft, ancient whisper stretched across the entire sky. When we look at it, we are seeing the universe as a newborn, a time when matter and radiation were still entangled. That tells us not just where we came from, but why the universe looks the way it does today. And, this multi-wavelength universe has changed our understanding of everything. It has shown us how galaxies grow, how black holes sculpt their surroundings, how dark matter binds the cosmic web, how gas cycles through stars, how the earliest light still echoes across space. It's not merely technology. It's a new sense, a new way of perceiving the cosmos. But this raises a gentle, unsettling question. If each wavelength gives us only a slice, only a fraction, only a filtered truth, then how much of the universe are we still blind to? How many frequencies have we not yet learned to listen to? How many messengers, gravitational waves, neutrinos, cosmic rays, are waiting to be woven into this growing symphony? And, well, this is where the story naturally carries us forward. Because the universe is not just large, it is layered. And it may be far, far larger than the part we can ever observe. So, let us step from the wavelengths we know into the question of scale itself, into the unsettling possibility that the universe extends far beyond the cosmic horizon, that what we have seen may be only the smallest part of an unimaginably larger whole. And, as we step from the layered universe of many wavelengths, there's a moment, soft, almost hesitant, when we begin to sense that even this beautifully stitched mosaic is still only a fragment. Well, what we've seen so far, all the galaxies, all the clusters, all the webs and voids and ancient light, all the radiohydrogen maps and X-ray halos, they sit inside a boundary we did not choose. A boundary defined not by telescopes or technology, but by physics itself. It's the cosmic horizon. The idea is simple in words, but vast in consequence. We can only see as far as light has had time to travel since the universe began. That means the cosmic horizon is not the edge of the universe. It's the edge of our visibility. And, well, the visible universe is enormous. 46 billion light-years in every direction, a bubble of light expanding around us. But the true universe, the one beyond that horizon, may be much larger. Perhaps hundreds of times larger. Perhaps infinitely so. It's not just a matter of scale. It's a matter of existence. Imagine standing in a small meadow surrounded by fog. You see grass, you see trees, perhaps a river, and you think that is the whole landscape. But beyond the fog, the world stretches on. Mountains, oceans, deserts you will never glimpse. The cosmic horizon is that fog. So, when we say the observable universe might be 1/250th of the whole, we are making a gentle but profound statement. Almost everything lies beyond our reach. The universe could continue far past what we can ever know, shaped by the same physics, the same laws, the same cosmic evolution, but rendered forever unseen. And, the surprising thing's that we can still infer something about that unseen immensity. Well, the cosmic microwave background, that ancient afterglow from the early universe, carries delicate patterns. Temperature fluctuations so faint they vary by mere millionths of a degree. These patterns let us measure the curvature of space. and the measurements tell us space is flat, not curved inward like a sphere, not curved outward like a saddle. Flat to extraordinary precision. And a flat universe has a remarkable implication. A flat universe can be infinite. It doesn't have to be, of course. It could be finite but unbounded, like a vast cube whose edges loop back on themselves. But the simplest explanation is that space just extends, and extends, and extends. It's not that the universe is big. It's that it may not have an edge at all. And, well, if that is true, then the observable universe, the part we gently cradle with our telescopes, is only one region in an endless expanse. Not just small, vanishingly small. A fraction tending toward zero. But even if the universe is finite, even if it loops back on itself like the surface of a sphere, it would still be larger, immensely larger, than the part we can see. Because inflation, that brief and explosive expansion in the earliest sliver of time, stretched space far beyond the cosmic horizon. It blew up microscopic quantum fluctuations into macroscopic cosmic structure. It smoothed the universe. It flattened it. So, whether the universe is infinite or merely colossal, our observable bubble is only the smallest piece of a much grander whole. And, there is something astonishingly human about this realization. We grow older, clocks tick, and we begin to understand that our intuition, shaped by rooms and cities and landscapes, cannot grasp cosmic scale. The universe is too large for metaphors, too vast for imagination, too subtle for certainty. Well, and yet we keep trying. We keep reaching. We keep building instruments to extend our senses. And perhaps the question that lingers underneath all of this is quiet but persistent. If the universe is so much larger than what we can see, then what lies beyond the horizon? More galaxies, surely. More clusters. More filaments and voids. But could the physics change? Could the constants vary? Could there be regions where structure formed differently? Places forever hidden behind the accelerating expansion of space? And, well, this is where cosmology steps gently into philosophy. The acceleration driven by dark energy ensures that distant regions of the universe slip away from us faster than the speed of light, not because they move through space, but because space itself stretches. One day, even the galaxies we see today will fade beyond the horizon, leaving only the nearest cluster gravitationally bound to us. It's not the universe shrinking. It's our window narrowing. And yet, that very shrinking window hints at a deeper truth. The universe is far too large, far too old, far too intricate for any one species, on any one world, to perceive fully. And yet, the little we see is enough to infer the immensity beyond. Well, think of it this way. We see patterns in the cosmic microwave background. We see distributions of galaxies. We see gravitational lensing across the sky. And from these faint fingerprints, we deduce the existence of realms we will never observe. So, our knowledge becomes a bridge between the seen and the unseen. And if the universe is truly infinite, or even just enormously larger than the observable part, then perhaps the most humbling realization is also the most beautiful, that we are not at the center, not in scale, not in privilege, not in perspective. We occupy one tiny patch of cosmic real estate, a small bubble of visibility floating in a sea of space-time. It's not a limitation. It's a reminder that existence is bigger than comprehension. A reminder that wonder grows the more we learn. A reminder that cosmic knowledge is always incomplete, and that its incompleteness is what makes it meaningful. And, well, this leads us gently toward the final thought in our journey. Because if what we call the universe is only a sliver of a far greater expanse, then what we have been doing, through all these chapters, is not mapping a finished world. It is reading the first few paragraphs of a story that stretches far beyond the horizon of our understanding. So, let us step toward that final reflection, toward the realization that even after all our instruments, all our insights, all our science, we have only just begun to read the opening pages of the cosmic book. And, as we reach the quiet end of this long journey through the visible and the invisible, through the bright filaments and the dark horizons, there's a moment, soft, almost trembling, when we realize that we've been, all this time, reading only the opening lines of a story far greater than ourselves. Well, you see, we have mapped galaxies. We have traced the whisper of the cosmic microwave background. We have counted clusters and weighed voids. We have watched newborn stars ignite behind veils of dust, and we have listened to the echo of ancient expansion. And, even so, the truth remains humbling. That everything we know fits within a small circle of light carved out by time. We look up thinking we've glimpsed the universe, but what we've seen is a fraction of a fraction. The 5% that shines, the 5% that speaks in photons. The rest, this deep ocean of dark matter and the even deeper sea of dark energy, surrounds us, shapes us, carries the galaxies like leaves on a tide. It's not that the universe hides itself maliciously. It's that its language is older than our senses, quieter than our instruments, subtler than our models. And when we talk about the observable universe, this 46 billion light-year sphere around us, we must remember, it is not the universe. It is only the part whose light has reached us. Beyond it lies a vastness we cannot touch, perhaps hundreds of times larger, perhaps infinite, perhaps home to structures we will never map, galaxies we will never name, and histories we will never witness. And, well, what our telescopes reveal grows richer each year, yet the gulf between what we know and what exists does not shrink. It widens, because each discovery only pulls back the curtain slightly, revealing not an answer, but a deeper corridor of questions. The cosmic horizon retreats as we advance, not because it moves, but because our understanding grows, stretching our imagination into realms we once considered impossible. So, what are we left with? Not certainty, not completeness, but wonder. The universe is not a puzzle to be finished. It is a landscape to be walked, slowly, reverently, knowing that most of it will remain forever beyond the next hill. And maybe that is precisely what makes our moment so extraordinary. We are a species that evolved on a pale world circling an ordinary star, yet somehow we've reached out with mirrors and equations to touch the fire of creation. We've measured the trembling of space-time. We've traced the faintest galaxies at the dawn of time. We've mapped voids 1 billion light-years wide, and we've begun to unravel the invisible architecture holding everything together. It's not just science. It's a testament to curiosity, a testament to the human need to understand the night. And, even though we have glimpsed only a tiny corner of the cosmos, that glimpse is enough to transform us, enough to remind us how small we are, yet how remarkable it is that we can know anything at all. enough to show that the universe does not yield its secrets easily, but it does reward persistence with beauty. Beauty so vast that it stretches beyond metaphor. We grow older, clocks tick, civilizations rise and fall, but the universe remains patient and ancient. And here we are, in the briefest flicker of cosmic time, reading starlight like scripture and building instruments that let us peer billions of years into the past. Perhaps the greatest revelation is this. The universe is not static. It is not a completed drawing. It's not a picture hanging on the wall. It is a canvas in motion, a work still being painted, a story still being written in hydrogen and gravity and time. And, well, the part we see, the galaxies, the nebulae, the arcs of light bent by unseen mass, those are only the first strokes. The rest of the canvas remains blank to our eyes, waiting for the future, waiting for newer instruments, waiting for minds not yet born to extend the edges of knowledge further than we can imagine. So, as we close this chapter, we don't close the universe. We simply acknowledge our place within it, small, curious, temporary, yet capable of wonder that spans billions of years. And perhaps that is enough, because the universe is not a finished map. It is a painting unfolding slowly in the dark, and most of the canvas, vast and silent, is still waiting for us to discover it.